Okay, here's a video I found on YouTube of some random dude with a solenoid. He plugs the red cord into the bottom and is tracing the current. See his hand? It shows the magnetic north pole is going to be at the top of the solenoid. What he's going to do is he's going to put some compasses around the solenoid and then turn his solenoid on.
As suspected, currents flowing this direction, north, attracts the south, the white. The magnetic field lines go from north to south, and the red is pointing, the red, which is a north pole, is pointing towards the south pole. Now watch what happens as I move this compass from one end to the other. Let me just move that out of the way.
All right, Mr. Dude on YouTube, that was pretty cool. Thank you for that. So let's explore mathematically that current that he was showing you, the current in a solenoid, and how it creates this magnetic field. The magnetic field inside a solenoid can be found using your right hand, just as we've been doing this whole time. So he attaches the red end of his power source and the black end of his power source to the other side. Thus, you can trace that the current is going through our system like this, and then you can take your fingers and you can wrap them in front of your thumb with your right hand. And as you do that, your thumb is going to be pointed to the right. And so here is the north, the magnetic field direction, in to the south and out of the north. And mainly when we deal with solenoids, we're interested in the magnetic field inside because it comes out to be uniform, which is kind of a neat idea because with a bar magnet, the farther or closer you go to the poles, the magnetic field will change. But here in this center region of the solenoid, no matter where you go on the inside, whether you are looking closer to the edges, the top edges, the side edges, or just in the very center, the magnetic field is actually going to be uniform, flat line. And longer the solenoid, better the results. So we can use Ampere's law to prove the equation for a solenoid. Here is the equation we will be proving, BS. Magnetic field of a solenoid. You're going to have mu naught, the classic 4 pi times 10 to the negative 7th. Then you're going to have little n and I. Little n is denoted as turn density, the number of pieces of wire per unit length. So thinner the wire, the more dense you'll be able to get it. And then our current I is just the one that will flow through our solenoid. So what I've done for you here is I've taken a solenoid and I've cut it in half. Well, I took a picture of a solenoid that was already cut in half. And we're going to just apply Ampere's law by making a closed loop. This will be different than our other loops because we will make a loop that will mock the symmetry. And in this solenoid, if we take our hand and wrap it around, we'll put our fingers going in on the top and out on the bottom of our thumb. And to do that with your right hand, you'll realize that your thumb is going to be pointed to the left to do that. And it's a straight magnetic field. It's not curling, right? It's your thumb pointing. Your thumb is straight. So what we're going to do instead of making a circle is we're going to make some straight lines. Okay, so we've done something like this before. In a capacitor, for Gauss's law, we used that kind of cylinder. We used the end caps. We could have also used a cube. Wouldn't matter. Okay, so here, there are actually 3 sections of this integral to evaluate. You're going to have the section from A to B, and then you're going to have the section from B to C, C to D, and D back to A. And so as we begin to think about the B dot DL, where is there a B? There's a B in this region, between A and B. So this is a valid region to evaluate B dot DL. And our B is to the left, and we'll make our DL also from A to B, also to the left, so that this dot product comes out as positive. We'll be able to rewrite B dot DL as just B times the length, L, the length from A to B. Let's look at the other integrals that we've set up. So from B to C, what are we doing there? Well, there's a magnetic field over here in the first chunk of that region, but it's perpendicular. It's at 90 degrees. So the dot product produces a 0 result for us. That comes up again when you go from D to A. Now from C to D, The magnetic field that we create, yes, there is one outside, but as you make your solenoid more and more ideal, then the magnetic field on the outside just approaches zero, because you'll have basically the idea of opposing magnetic fields from either side. And so the b's will cancel out to be zero, in which case our integral just becomes zero because b is zero. Okay, so let's try that. So the only one we're going to evaluate is from a to b. And when we do integral b dot dl, we get bl. Let's think about the I we enclose. So if we're looking at the I inside of this loop, 1, 2, 3, 4, 5, 6, 7, 8. 8 loops of wire. I enclose 8 I's. Or if I made my square a little bit bigger, I can enclose 9 I's. So it all matters the size of my square compared to how densely packed the solenoid I's are. So I guess that I could rewrite the I that I enclose as the current I times the number of loops inside, n. And again, the number of loops inside is just going to depend exactly on how long I make my loop. So when you simplify, you'll get B equals mu naught I n over L, where L is the length of your Amperian loop. And n over L will reflect the turn density, and is represented oftentimes with little n. Congratulations, you have derived using Ampere's law the magnetic field of a solenoid.